Okay, so we are demonstrating side channel attack system here, and our system is to test embedded systems for side channel vulnerabilities and solve them. So here we have made a test system where we have a password checking or keyword checking, where we are sending a text string via UART, and this function will be comparing it with the secret key, and it is also turning on and off an LED. So here in the first demonstration we will be showing how we can extract information about the secret key by looking at the timing of this LED turning on and off. So here we have the waveform of the LED, and so here if I'm entering some random string via UART, I'm recording the width. So the width is almost 67 microseconds. But when I'm sending the correct key, you can see that the width suddenly increases. This is because of the timing dependence of the function, the check key function, on the input we are sending. So here in this example we are detecting if our password has matched, but actually if we are able to enter this the partial password itself, then also the timing will be different from entering a completely wrong password. So with the system that we have developed, we can emulate a timing side channel attack, and we can characterize the timing behavior of any piece of embedded code. So here I have the same password or string matching function, and I am able to feed inputs from a Python program and characterize the timing of this. So first here in the code I have to enter some test code which will get the inputs, and it will feed it into the checkpass function, and it will time the checkpass function and send it back via UART, which will be recorded by the Python program. So here is the Python program, and I am characterizing the timing, and I know the password, so I'm giving different combinations. First, if we are looking at this, we can see that when we are giving random guesses, when we give a guess that has the same length as the final password, we are getting an increase in timing, and from that we can detect that the length of the key is matching. And then when we are giving just one first key same as the final pass key, we are able to again see an increase in the timing. So like this we are able to detect how many letters in our string have been matched with the internal keyword. So next we made an algorithm to do this side channel attack from scratch, and if we run this we can see that it is able to crack the password by detecting the change in the number of cycles, and it took this many number of attempts. And next we tried to improve the algorithm. So essentially the reason that we are able to do this is because the function returns the moment it detects a change in the key from the internal keyword. So we removed that, and we implemented a flag based approach where we are anyways running the same number of iterations, but again when we characterized it, we were able to see uh, a slight change in the timing. The difference in timing is just an order of 1 or 2 cycles, so it is much more difficult to do the attack, but nevertheless we were able to extract the password. And next we um, now essentially the reason that we are able to do this is because of the branching behavior in hardware, and we removed the branching itself and we implemented it as a logical and operation. And here as well we are able to see a slight timing difference. So we change the logical AND operation with a bitwise AND operation, and finally when we are running it, we are seeing that regardless of the input, the timing is same, and we cannot use the timing to extract any information about the input. So if we change this function and run it, I can show in real time that now it has extracted the timing, and it is now attempting to break the password with the same algorithm, and it was not able to find the password because the timing is same regardless of the input. So next what we attempted was a timing side channel attack on TinyML, and specifically we tried to attack the ReLU implementation. And here we are using the same exact framework, but we have just changed the function that is being run, the timing of which is being extracted. And when we extracted the timing of the ReLU implementation, we were able to see that depending on if the input to the ReLU function was less than 0 or greater than 0, the timing is different. And again, when it is part of a network, we are able to extract the input crossover by giving all giving all combinations of the inputs. We are able to extract the input crossover point, which is the point where the time the ReLU function activates. So from this we can find the weights and bias of the network itself. So to solve this, we change the implementation of the ReLU itself by implementing a mask based approach, a mask and bitwise and operation based approach instead of the conventional branching approach. And when we are characterizing the timing of this, we can um, see that the timing is not dependent on the input, and so the network parameters cannot be extracted by timing side channel attack.